Have you ever wondered why time seems to flow in only one direction? Why spilled glass shatters, but the shattered pieces never spontaneously reassemble? Today we're going to explore a fascinating connection between two areas of physics: entropy, a core concept in thermodynamics, and special relativity. While they might appear unrelated, entropy plays a subtle but crucial role in how we understand time. Entropy, often denoted by S, is a measure of disorder or randomness within a system. Think of it in terms of organization. A neatly organized desk has low entropy, while a messy desk has high entropy. Similarly, a crystal lattice has low entropy, while a gas uniformly spread throughout a container has high entropy. We see entropy in action all around us. Ice melting into water is an example of increasing entropy, as the ordered structure of ice transitions to a less ordered liquid state. Mixing two gases also increases entropy, as the gases become more dispersed. Even the aging process in living organisms can be viewed, in a broad sense, as a consequence of increasing entropy within a larger system. The second law of thermodynamics is paramount. It states that the total entropy of an isolated system always increases over time, or remains constant only in idealized reversible cases. This means that spontaneous processes tend to move towards states of greater disorder. A dropped glass shatters, increasing entropy, but the shattered pieces never spontaneously reassemble into a glass. This would decrease entropy, violating the second law. The second law gives us what we call the arrow of time. It explains why we see movies running forward, not backwards. We see eggs breaking, but not unbroken eggs spontaneously forming. This directionality of time is deeply connected to the restless increase of entropy. Now let's shift gears briefly to special relativity. As you know, special relativity deals with space, time, and the behaviors of objects at high speeds. One of its key predictions is time dilation. Time passes differently for observers moving at different speeds. A clock moving at a high velocity relative to a stationary observer will appear to tick slower. So here's where the surprising connection emerges. While the basic laws of thermodynamics still hold in relativistic situations, the way that we describe entropy can be affected, particularly when we consider the role of information. Information theory, which is tied to entropy, becomes important here. The amount of information we have about a system is connected to how disordered it appears to be. In relativity, events that are simultaneous to one person might not be to another. This means that different observers might have different information about the same system, which can influence their understanding of its entropy. Importantly, even though observers might disagree about entropy, the actual entropy of the system, measured by someone at rest with the system, still follows the second law of thermodynamics. The early universe presents a fascinating puzzle. It is believed to have been in a very low entropy state. Why was it so ordered at the beginning? Understanding the interplay between gravity, space-time, and entropy in the early universe is a major area of ongoing research, and special relativity is fundamental in our cosmological models. Let's consider a classic thought experiment. Imagine a gas confined to one side of a box, with the other side a vacuum. When the partition is removed, the gas expands to fill the entire box. Why? The gas expands because there are vastly more possible microstates for the gas molecules when they are spread throughout the box than there are when they are confined to one side. The system evolves towards the most probable state, which is the state of the highest entropy. How does entropy relate to time travel paradoxes? Why do many physicists believe time travel to the past is impossible? Well, time travel paradoxes often involve changing the past, which would require reversing processes that have already increased entropy. This reversal would violate the laws of thermodynamics. It's like trying to unbreak an egg. The increase in entropy provides a strong argument against backwards time travel. So, we've journeyed through the realms of order and disorder, explored the strange landscape of relativistic time, and discovered a surprising connection between them. We've seen how entropy, the restless drive towards disorder, gives us the arrow of time, and how this fundamental principle intertwines with the relativistic nature of spacetime itself. It's a connection that challenges our intuitive understanding of time and opens up fascinating questions about the universe's past, present, and future. But the story doesn't end here. The interplay between entropy and relativity is a field of ongoing research, full of unanswered questions and exciting possibilities. What role does entropy play in extreme environments of black holes? How can we reconcile the low entropy of the early universe with our current understanding of physics? There are just some mysteries that continue to drive scientific exploration. So, the next time you see a glass shatter, or gas expand, or even just feel the passage of time, remember the deep connection to entropy. And when you contemplate the vastness of the cosmos and the strange behavior of time at relativistic speeds, remember the surprising role that entropy plays in shaping our universe. It's a reminder that even the most seemingly simple concepts can lead us to the most profound discoveries. Uncover the universe's secrets with She Explores the Cosmos. Like and subscribe to join the journey.